Hi, I'm going to go over 3 minimization problems in this video, and with Geogebra I'm going to show a little bit of graphical analysis, and then we'll also look at some calculus and algebra on how to minimize these word problems, or how to work with word problems about minimization. In the first one we have a fence, and our fence is alongside a river, and so the river forms one side of that fence. The other two sides, we have to pay for the fencing. So we've got a river, we've got a regular rectangle, we've got 4 corner posts, 2 along the river, 2 over here. X is going to be the side running perpendicular to that river, and then we've got a Y over here. And it says our corner posts are $25 each, $25, and then our side running parallel to the river is $5 per foot, $5 per linear foot. And over here we've got $8 per linear foot. And so we want to find out the minimum cost. We want to write the function that best describes the cost, find the domain, and use the graphical utility, find the minimum cost, and then the dimensions, of course. And so what we know then is the area in here is 1,000 square feet, and so 1,000 square feet is equal to the length times width, or xy. Now, if we're trying to find the minimum here, then we want to rephrase this so that we're working with only one variable. So let's rephrase y in terms of x. Y is then equal to 1,000 over x. And so now we can start to write c, which is our equation for the cost of the fence by square foot, or by foot, by linear foot here. So we've got 16x because 2x plus y is equal to the total length. And then we're going to assess that on the basis of the cost per foot. So we've got 2 times $5 per foot times the number of feet, which is x. Sorry, that's $8. That one is $8. There. 2 times $8 per foot times the number of feet plus $5 per foot for y, but y is rephrased in terms of x, or 1,000 over x. And then we're going to add to that the 4 posts, which total $100, 4 times 25. And so there's c of x. C of x is 16x, 8 times 2, plus 5,000 over x, 5 times 1,000 over x, plus $100 at the end there. And first thing, let's look at the domain. The domain. And so if we zoom out of this, we've graphed it, right? So we got this graph is c of the x, or the cost as a function of the length of those sides, right? And we can see that it looks like the y-axis is a vertical asymptote, and then we also have a slant asymptote here. Right, and as we zoom out and zoom out and zoom out and zoom out, it just looks like a line. It looks like a line across there. And so we don't see anything on the vertical, we just see what looks like a line on the horizontal there. And so we can assume that the domain does not include x equals 0. And we know that because if we divide by 0 here, we get undefined. So we can assume again that y-axis is a vertical asymptote, and then if we look for the limit as c of x, limit of c of x as x approaches 0 from the positive, what we end up with is a very small number here, a very small positive number. We get 0 here, 100. This is going to trend towards infinity, right? Infinity, and that corresponds to what it looks like is going on in the graph. X, the function increases rapidly towards 0. And then it looks like if we approach that from the other side, as x approaches 0 from the negative, it looks like negative infinity. And that's because we've got a very small negative number here. So 5,000 divided by a very small negative number is negative infinity here, and that's what it looks like on the graph. Right, and then as x extends out into the horizon to infinity, what we get at is the limit c of x as x approaches infinity. And so we're going to get a number divided by infinity that trends to 0, a constant times infinity, that's infinity, and that constant is no longer important because relative to infinity, it's not making a difference. So x equals infinity, or c of x equals infinity. And then on the opposite side, which really doesn't matter because when we're talking about cost, these are not real values here. Nobody's going to pay us. We're not going to have a negative cost. That's impossible. But since the function does include these, our actual domain is all in the first quadrant here because we're all in the positive x. But just to be thorough, that trends to negative infinity because we've got constant times negative infinity there. Right? So there's our domain. Now let's try to solve for the lowest possible cost. This is sort of a practical problem. Right? We want to find the dimensions and the lowest possible cost. Now what we can do on a graphing utility is plot a point and kind of trace that along and zoom in and then trace that along and try to find the lowest possible y value and then record the x value for that lowest possible y value. But on Geogebra here we've got the opportunity or the function where we can just plot the minimum, plot the extrema. So we get c. And c is at 17.68 and looks like 665.5.69. So at 17.68 is our x. X equals 17.68. And that means that y, that's feet, y then is equal to 1,000 over 17.68 or roughly 56.56 feet. So there's our dimensions there. And even if we didn't have this graphing function here, this graphing program, what we could do is evaluate the first derivative of x, of c of x, the first derivative at 0. All right, if we wanted to evaluate the first derivative, we can see this plots the slope of the function. And then we can see it crosses the x-axis. Crosses the x-axis right around that same point, 17.68. And just to make sure, let's look at the point there, which is the root. The root, Geogebra offers a root function, so we're looking at the root here. The root of the derivative is at the same x value as the minimum. And that's no surprise because the minimum is a slope of 0, and if the derivative plots the slope, then the derivative will go a 0 value where the slope is 0 right at its minimum. Right, and so if we have c of x is equal to 16x plus 5,000 over x plus 100, then the first derivative, c prime of x is equal to 16 plus negative 1 times 5,000 over x squared. Right? Making this into 5,000 times x to the negative 1, we'll use the power rule, and that's fairly intuitive if you know anything about derivatives. Right, and so we want to assess that at 0. Where does that cross the x-axis? So 0 equals 16 minus 5,000 over x squared. We'll multiply by x squared, and we get 0 equals 16x squared minus 5,000. So 5,000 equals 16x squared. We'll divide by 16, divide by 16. And then after that, we'll take the square root. And that will give us x. And magically, we get that same value. And so we can see our minimum cost is at that point, right? Our minimum cost, then we can plug x back into this function and get our cost, knowing that that's the length of x we need to get that minimum cost. Right, so moving on to the next problem. Let's look at minimizing surface area. So the UPS has contracted. You design a closed box with a square base that has a volume of 10,000 cubic inches. See the illustration. It's not a cube. We can see the bottom and top are squares, but the height here is different from the length and width. And so we want to find the surface area, graph the surface area, what's the minimum amount of cardboard that you need, what are the dimensions of the box. Working with what we know that x times x squared y is equal to the volume, or 10,000 cubic inches. And let's just solve for y like we did before, 10,000 over x squared. And then we can find the surface area. SA is equal to the sum of the areas of the sides. So we got 2x squared for the top and bottom, plus 4 times xy. And remember, y is 10,000 over x squared. So we can get rid of that, get rid of that. All right, there's our surface area, and I've graphed that. Here on Geogebra again. And we get 2x squared plus 40,000, 4 times 10,000 over x. So as x approaches 0, the volume stays at 10,000, but then y must become very large. It would be a very tall, very small box. I don't know what you would put in there, perhaps a very, very large, long pencil. Y similarly trends to infinity. We can't divide by 0, and so 0 is not within the domain, right? So we're moving along. Let's look for the minimum value. I've plotted that using extrema on Geogebra here. Right, there's our extrema, and then same thing if we wanted to find that using pencil and paper, we could also do that. We just have to take the derivative using the power rule. So if we've got, this is y, 2x squared plus 40,000 over x, then if that equals y, so then y prime is equal to 4x plus negative 1 times 40,000 over x squared. Right, and we can rationalize this, make this a rational expression by multiplying by x squared. In the first term, we get 4x cubed minus 40,000 over x squared. And then on Geogebra, we can plot the root of that. And we're going to get that same point, right, where our x values match up. So 21.54 is the number of centimeters, 21.54 centimeters for the length of x. So that's the top and bottom of the box. And then that means we can solve for the remainder. 21.54 centimeters is our desired value there. Amount of cardboard, well, that's just the surface area, so we'll plug in 21.54. We can solve for y using 21.54 here. Right, and then the dimensions are just 21.54, 21.54, and then 1,000 divided by 21.54 squared for that one there. And so why might USPS or UPS be interested in designing a cardboard box which minimizes the surface area? Well, to minimize cost. I think that one's fairly straightforward. Let's look at one more problem. Again, minimization. So in our final example, here we've got the cost of a can. We're making some kind of soda or soup can here. So we've got a cylinder, just a basic cylinder can, radius on the top and bottom, height on the side here. We know the volume is equal to 500 cubic centimeters, half a liter. Volume equals 500. And we know that's equal to the area of the top, which is pi r squared, times the height, pi r squared h. Let's just go ahead and solve for h there like we've done in the previous examples. So then h is equal to 500 over pi r squared. So we can find the cost is 6 cents per square centimeter on the top and bottom. The sides are 4 cents per square centimeter. And so our cost as a function of x, we're going to say x is actually r. Cost is a function of r. is, so we need the surface area. So we've got pi r squared on the top, pi r squared on the bottom. So 2 pi r squared times 6 cents per square centimeter. And then we're going to add to that 2 pi r for the circumference of the top times the bottom. If we roll that out, we can get sort of like a rectangle shape, which is the circumference of the top times the height. So we get 2 pi r h. Remember, h is 500 over pi r squared. We can get rid of the pi r here. There we get 2 times 500. And then we're going to multiply that times 4 cents per square centimeter. I graphed that out on Geogebra here. Right, we get 12 pi x squared or r squared. So 12 is 6 times 2 pi r squared there, times 4,000 over x. 2 times 500 is 1,000 times 4 is 4,000 over x. Right, we get the same sort of deal here, where obviously our volume, our cost is not going to be 0. Our domain does not include the y-axis. It goes to infinity. And then we're going to solve for this minima here. I've already used the extrema function on Geogebra. And so again, we could solve for that derivative by hand if we wanted to, taking f prime of x, or sorry, taking f of x as 12 pi x squared plus 4,000 over x. Then f prime of x, we're just going to use the power rule as we did before. Drop down that 2, we get 2 times 12 is 24 pi x plus negative 1 times 4,000 over x squared. Now we can simplify this, or when we solve for the root, we're going to have to multiply by x squared. We can rationalize the entire expression, or we can multiply by x squared at this stage. X squared times 0, of course, is 0. So 0, we're looking for the root again. So 0 equals pi x cubed then, minus 4,000. And so we can move that 4,000 over to the other side. Or we could have done that first anyway, it doesn't matter. So we get 4,000 then equals 24 pi x cubed. And thus we'll just divide by 24 pi. We'll take the cube root and divide by 24 pi here to get rid of that. And we get x equals 3.76. Same as Geogebra did for us in an instant here. Right? So, but if we don't have these graphing utilities, for example, on a test or out in the real world, then we need to do things by hand. Also, the people who develop the graphing utilities most certainly know how to do stuff by hand and then input that into the computer such that the computer can do all the legwork for us here. Most importantly is that we understand the concepts, so we be conceptually literate. Understand the idea that the minima here, we've got decreasing slope on the left side of the minima, we've got increasing slope on the right side, so that means that the derivative will be negative and then positive on the right, on the left and right of that minima. And then the root of the derivative, where the slope equals 0, we're going to have that same point at the minimum. And so going back to the can, our desired outcome here, our minimized, what's going to minimize the size of the can or the cost of the can? Here is, we have a radius of 3.76 centimeters. That'll give us the cheapest can possible, right? And so maybe tonight go home and measure a soup can, measure a soda can, and if it follows this same sort of pricing structure, where it makes sense the top and the bottom are stronger material, they're thicker metal. Makes sense the sides are not as thick, so they would be cheaper. So this is a real-world example where people, whether in business or an engineering department, at Campbell's or Pepsi or whatever, are trying to make a can, they want to reduce the price as much as possible. They need to know the minimum value here given the prices. They know the prices because they source the material and they get prices per square centimeter, per square meter, or whatever. They know the rough dimensions of the can, or they know how much of the product they want to give the consumer. 500 milliliters would be the size of this one, right? Half a liter, it's 500 cubic centimeters or 500 milliliters. And so then they want to minimize the cost of the can to give the consumer this much product, given these two costs. It's a practical, real-world problem. It can be solved a couple of different ways, again, using Geogebra or graphing utility. But if we try to zoom in and then plot a point without calculus or without some sort of function via this graphing utility or a calculator or something like that, it would be imprecise and time-consuming because we could zoom in and then we're going to find minuscule differences as we zoom in, moving that point to the right or left. As we zoom in more and more, we can get close to or we can approach that minimum, but it's unlikely that we're going to get it with the precision and accuracy and reliability that we would get just using the calculus or using one of these extrema zero functions on a graphing calculator or something like this. Okay, so we'll continue to look at more topics in algebra, geometry, and calculus in future videos. Thank you.